Hello. So here's the equation of motion for the Jeffcott Rotor model, including damping. You have your mass matrix, your damping matrix, stiffness matrix, and then forces on this side. And we could solve this by decoupling the matrices, but it would require complex eigenvalues and eigenvectors. So to avoid this, and also because presumably the damping is pretty small, we can neglect the damping terms, and the equation of motion simply becomes this, which has a decoupled mass and stiffness matrix. And this is beneficial because you can just separate each degree of freedom into its own differential equation, and then assuming that x and y are simply some magnitude times cos omega t or sine omega t, you can plug these into these equations here and solve for x of t and y of t. And then in order to validate the results from this model, I basically just created a system with known values for the mass and stiffness, and then plotted x as a function of time for 3 different angular velocities. And this was able to show that the behavior of the model in the subcritical and supercritical regions is very consistent with the theory.